Okay, ladies and gentlemen, so we have a model that is of growing sophistication. One of my original plans was to add in heart disease with this model explicitly. So rather than having it be merely a latent factor when talking about the impact of cumulative time smoking, we'd actually have a heart disease state that someone could be in. They reach that heart disease state, in which case we could take that into account as a factor in increasing their risk of death, that controlling for cumulative time spent smoking. And we may yet do that, but my point here is to introduce to you new skills as well. And there's one that we really haven't delved into, but is an absolute essential. To wit, interactions of individuals with their environment. So, like to hit this. Okay, ladies and gentlemen, any logic provides the ability, as reflects the motivations for and the emphasis of agent-based modeling, for allowing agents to interact with their environment. This is one of the primary distinguishing features and emphases of agent-based modeling when we compare it, say, against discrete event modeling, both being individual-based traditions. But discrete event modeling is a very narrow notion of how people interact. You have agent interactions, entity interactions consisting of weighting, and then you have these distinguished resources who may in fact have a certain agency, doctors, nurses, allied health professionals that might interact with a patient in a certain capacity of serving as resources for them to be processed. But in agent-based modeling, we have this real emphasis that agents interact with each other and they interact with the environment potentially more broadly. That environment could be a spatial environment, a layout of a facility. It could be a geographic environment, a certain situated geographic area. And some examples I've provided illustrate each of those. We'll be tapping into those more. Right now, I thought we'd add in a network. Okay, a network of people. We'll also start to tap into the spatial environment associated with any logic and use it to shape the network. Okay, so let's use this time to do this. Okay, so I'd like to begin by doing two things. Number one. Okay, I'd like to go to the palette, the agent part of the palette, and have person up, and I'd like to add in a new aspect of heterogeneity for a person. Okay, this is going to be socioeconomic status. I'll call it socioeconomic status. It'll be a double precision value between 0 and 1. Okay? 0 and 1. You might alternatively prefer to think about socioeconomic position, but for now I'll use SES. Okay? Now, what we did is nothing short of revolutionary from a broader perspective of modeling, in the sense that we're adding in heterogeneity in a very localized way. One of the issues with aggregate models is if you have an aggregate model, perhaps it's a model of individuals at different points in osteoarthritis spectrum, individuals who are yet unafflicted, those with mild or severe, individuals who have received surgical intervention, etc. We can match a model like that. Now, if we needed to add in an aspect of heterogeneity, let's suppose sex of a person, we actually need to take that model, this aggregate model, and we essentially need to duplicate it for that new sex. Now, there's ways of doing this that are less visually intrusive. We do what's called subscripting of each stock and flow, and many of the variables, the dynamic variables will depend on them, will also typically be subscripted in many cases, unless they're aggregating up. But it basically can double or go a long way towards doubling the size of the whole model. And it's a global thing. You have to do it systematically across all these areas to add in this one aspect of heterogeneity. If we want 17 age categories, 5-year age categories and 80 plus or something, we need to stratify the model by these age categories and multiplies it 17 times larger. The point is that in terms of ability to do it, it's a heavyweight operation. It actually takes effort across the entire model to do this. We systematically go through and add these things in. And as a result, in aggregate modeling, it's cumbersome to even investigate the impact of heterogeneity because it's so big an undertaking to really add it in systematically in a thoroughgoing way. And there's other ways to try to probe how sensitive it might be, but basically adding heterogeneity is expensive, it's intrusive, it has global implications, and it's something we can't do lightly. Here we've just added this aspect of heterogeneity. We could take it out with quite some ease later if we wish to do so. So, SES. Ladies and gentlemen, SES. It's a double value. Now, if we went and we tried to build this model now, what would happen? Would it be a happy camper? No, what would happen? Yeah, it would complain, in fact, bitterly. It would say basically every ad population it doesn't know what to use. Really, to be clear, we should probably specify a default value, but that's not going to get us very far. We could specify a default value for this, but what we really need is something more than that. We could say default value of 0.5, but that's still not going to help with this issue. The default value is just a value if we don't fill it in, particularly in that case of the population, for that initial population, what is it going to use? This is not really a good thing. We need to fill things in. So let's go and apply ourselves to this task. So let's go to population. Okay, population. And I'd like to go to SES here. And we could go add an empirical distribution. You know how to do that. I'm just going to say uniform between 0 and 1.0. Okay. You know how to add distributions now. I don't think we need to take the time. There's too big an opportunity cost. Okay, so first of all, I've set it to be uniform. Notice what was there before was 0.5. That was the default value. It just substituted that in because we didn't specify anything. But it's not particularly deep. Okay, that's one thing. Now we have to go each place that the agent comes into the population, these add populations, and we need to add that in. The reason it's complaining is, well, it shows you right here. Now it's expecting a final double value. This is the SES. It's expecting us to tell it what SES to use. And for immigration, we might have a somewhat different SES, right? Maybe those who come into the population are of higher SES because they're selected by certain skill sets. After all, I know from personal experience that one has to apply and make an arguments for why Australia would benefit from skill sets. I recently made the case. I'm not sure it would have passed the test. Whether Australia would benefit from. Sorry?
It fell on deaf ears.
Okay, so ladies and gentlemen, here we could draw from a different distribution. Let's imagine the immigrants coming in are somewhat higher SES in this case. We'll draw from uniform between 0.5 and 1.0. Or we could draw from a beta distribution, right? Between 0 and 1 if we wanted to. That wouldn't be a bad idea. But again, my goal here is not to dwell on distributions. We could always use an empirical one for immigrants where we have data. That's great. I'm just going to put this down here for now. Okay? Ladies and gentlemen. Good. Okay? Next, where else can a person enter the model? Pregnancy, indeed. And that lives in person because it's a mother who gives birth. And here we are going to go to this, and we're going to go to where the pregnancy, there's a delivery of the child, and we are going to assume that the child, for simplicity, we'll assume the child has the same SES status as the mother. I'm working towards, I often have multiple goals in introducing things. I'm working on multiple fronts at once, and this is partly going to be something that will work towards a question that Rod asked. Okay? So we're passing on the mother's SES, my SES, it's the mother who's delivering, as a characteristic for the baby. What we're passing here to add population is the characteristics, ladies and gentlemen, of the baby. And for this, we're passing on the mother's SES for the baby's SES. Are we okay with this? Good. Okay, ladies and gentlemen. Great. So I would argue now we're probably ready to go with this model. Let's build it. Things are happy. Let's run it, if we may. Okay? Okay? Here we go. Okay? Here we go. So now we have these individuals, and if we look down, we'll see that each person now has an SES. Okay? Fair enough. But I want to do something more than that. I want to lay them out by SES visually. I want to establish their location by SES. Okay? Are we ready to do this? Okay. Hearing no objections, I'm going to go to main. And within main, I'm going to go to population. There's actually two ways to lay things out in AnyLogic. There's kind of a restricted but quite easy way, but it's restricted in its implications, and there's a general way. Let me introduce both to you. May I do that? Okay. So for main as a whole, the sort of easy but restrictive way is you go and you scroll down in the enclosing object. In this case, it's main. Okay? And you scroll down, and there's an area called space and network. Do you see that? We'll enjoy the closer pleasure of its acquaintance soon enough. But for now, space and network, I'll simply draw your attention to the fact that the layout type here can be set to be random. Do you see that in space and network? And that would set the people to have a random location in space. But in fact, we already arranged for that in a better way. That would have allowed us, or would have laid them out in space, but we wouldn't be able to shape that distribution. It would be a uniform distribution over the delineated 500 by 500 space. We don't have a way of shaping that by characteristics of them. Maybe we'd like to have their locations, for example, reflect their characteristics, have men and women grouped spatially, or people grouped by SES, or by age. Okay, so let's see a more general way. So you can do that, and that's really good for quickly laying things out. What that will not capture is spatial distributions based on characteristics, and what it will not capture, mark my words, is incoming populations, births, immigration that are coming into the model. For this, the more robust way to do it is through population. The population to which those people are being added. And you will notice here that we have here an initial location. See it yonder? And we can scroll down here, and you can see right now we had put in the opening minutes of our first encounters with AnyLogic, we had put in a bit of logic about where people are located. You see that? Now, if we're dealing with a geographic model, as we will sometime soon, this would actually be coordinates for latitude and longitude. We'll ask us for the latitude and longitude of the person. For here, we'll deal with more abstract component, and we'll go into the to the GIS at a later point when lunch doesn't confine us. Okay, ladies and gentlemen, now what I'd like to do is for this to say the following. We'd like to have their X position be based on their SES. And the way in which you do this is quite common in my experience. The way in which you do this is the same way if we had, for example, SES wanting to depend on sex or an earlier characteristic. We could refer in this formula, in fact, to these earlier ones, okay? And the way in which we'll do it is the same. What we'll say is self dot in that name. In this case, self.ses. If SES depended on sex, we could make this distribution, the parameters for it, depend on self.sex. And it will be a happy camper. Okay, so make it self.ses times times, I'll make it times 1,000 if I may. Ladies and gentlemen, 1,000. Okay? 1,000.0. There we go.
This use goes up to 1.
It does. So this is going to be between 0 and 1,000. Yeah, I'm going to make it for visual reasons. I'm going to make it a bit bigger. Good call. Okay? Can we run it? What should we see now? Well, people will be sorted by SES over a broader area. Who are these folks over here? They are richer individuals. These folks down here are poor individuals. We'll come back to that, okay? Ladies and gentlemen, given an SES like this, could anyone anticipate, could we make, for example, likelihood of initiation depend on SES? Very readily, much in the same way that right now it depends on age, or much of the same way death depends on several things, cumulative time till smoke, their current smoking, age. We could have initiation depend on SES. Could we not? Yeah. Okay. Okay. So here, ladies and gentlemen, we're going to, Joanne, I have a solution to your problem with the phone. Okay, yeah. Yeah. Okay. So ladies and gentlemen, we could do that, but our goals are a little bit different right now. We've laid people out by this. Next, we are going to impose a network whereby people who are less have lower incomes are more likely to associate with those with lower incomes, higher incomes with higher incomes, okay? So this is what we're going to do. We're going to go to main, and we are going to go here to a network type that is going to be distance-based. So an individual will be connected with people who are within a certain distance of each other, okay? And the connection range will be 75, okay? 775. Are we okay with that? Okay, this is actually going to depend on a somewhat larger population, which we will impose. So people, any given two people, A and B, would be connected if and only if their distance in that space is within 75 units. Now, we can actually specify in AnyLogic what are the units for measuring distance. You'll notice if you go to main and you look up, there's something that converts the visual distance to physical distance. Do you see that in AnyLogic? And within a GIS context, this will be particularly significant. Let's go run this model, if we may. Let's run it with a smaller population, and then let's run it, ladies and gentlemen, with a larger. Okay, with a smaller population, well, we don't see much. And you might think, well, the network, I don't see a network there. Let's run it with 1,000. Hypothesis, maybe the network isn't shown because people aren't close enough together. With 1,000, people are packed, but still no network. The deal here is, ladies and gentlemen, there's a difference between imposing a network. There's actually a network there. Turns out there's a network there. Trust me, if I had more time, I'd show you it by having people's size depend on the number of connections. But it's just not shown. And there's a very simple reason it's not shown that rookies run into overlooking. Can I show it to you? So there's a logical separation between imposing a network on the one hand and showing that network on the other. What you need to do is typically you want to do both. I've just imposed the network with this rule. You see that AnyLogic actually has several types of networks that are supported, and we imposed one of them, to wit, a distance-based network. But now we're going to, in fact, adjust it. So let's go to person. If you go to person, you scroll up, you may see something you didn't even realize was there. Thing called connections. Do you see that? Now, in a health context, we're often concerned with multiple types of network. Familial network, perhaps collegial network. Family versus social network. Communicational versus proximate network. IDU network versus sexual transmission network for HIV. We're dealing often with multiple types of networks. And AnyLogic will in fact allow you to, from the palette, under the agent component, you can drag in more types of connections. Each will be distinguished. They can be an IDU connection, there can be a sexual network connection, and then a family connection is the default. But all agents come with a built-in network of these connections, okay? And those connections are the ones that are by default used if you're not explicitly mentioning other connections here. These are the ones that are wired up by, like when we chose distance-based network, okay? Okay, so for these connections, ladies and gentlemen, these are the operative ones here. For these connections, we can actually specify, for example, incoming messages, where do they get routed to? We'll go through messages, probably after lunch. But I'd like you to go to these connections, and I'd like you to go down to animation. Do you see the properties of these connections? Selected these connections, you go down, there's an animation area. See or not? See. Okay, let's choose draw line connecting agent. If we select that, we further have the option of saying, do we want to draw the line behind or on top of them? Okay? I guess to make it most obvious, I'll say draw the line on top. It'd be a little bit more tangly, perhaps, in its appearance, but it'll be obvious. Okay? So earlier we imposed the network. Now we're indicating, hey, the connections for a given person, which link them up with others. To what degree do we want to display them? And if we do display them, how do we want it to be vis-a-vis their representation? This is just display. It's not the logic. Okay, let's run the 1,000 size population. Here we are. People are knit into networks. Those networks are there before, we just didn't see them. Okay? If we run 100 size population, it will look less dense. Why will it look less dense here? Because people are not as close and it's kind of fragmented. Well, there's fewer people in the population, therefore it's less dense. It's less likely any two people will lie within a certain that 75 distance threshold, and it's fragmented. We're going to use a larger population. Are we okay with that? So again, what did I do? I went to person, I went to connections, within person, and I went to the animation area and I checked this box here. Are we okay? Okay, great. Good. We just imposed network structure, localized network structure. There's several other types of networks that are supported. If you go to main and you were to look down in main, you'll find that in addition to distance-based, AnyLogic offers built-in support for another localized type of network, to wit a ring lattice network. That's where each person is connected with a defined numbers of people. They're kind of ordered, and they're connected with some people just below them in the order, some people above them. Maybe one on each side in the most classic way, or two on each side. there's a random network where any two people are equally likely to be connected. This is what's called a Bernoulli random network, or a Poisson random network, or an Erdos random network. It goes by different names. Any two people, A and B, are equally likely to be connected regardless of where they are spatially. There's no ordering. That's extreme, the opposite of locality. Distance-based, ring lattice, very local in 2 and 1 dimensions respectively. Okay, their location in space in a distance-based network dictates to whom they're connected. For ring lattice, their kind of order in the ordering. They connect to other people in the ordering that are nearby them. Random network, there's no locality at all. It's global connections, willy-nilly. In the extreme of that is a caveman network, where you're connected with everyone. Small world network, ladies and gentlemen, is kind of a combination of a extreme globalness, any two people are connected randomly, with ring lattice, where you're only connected locally. So basically, most of the people you're connected with are local, typically the way the parameter is set, with only a small fraction, say 5%, connected with anyone. So you have just a small number of connections with people all across the network, but most of your connections are local. And that's how a lot of us live our lives. We have some connections globally, but most of the people we know are local, our neighbors, our family, our friends, right in the local area. And then occasionally you'll get strange global intruders who appear with unusual habits and accents and unusually demanding boot camps. Okay, scale-free networks, ladies and gentlemen, are type of network many of you have heard about. They exhibit, the name reflects the fact that regardless of whether you're considering individuals with few connections or individuals with many connections, the probability of having k connections compared to the probability of having 2 times k connections, regardless of whether it's 1 and 2 or 100 versus 200, that same, the ratio of probabilities is always the same. So this is a network with a long tail in terms of distributions. It exhibits a power law in terms of the number of connections, which means there's a small fraction of the most people have a small number of connections. A small number of people have very large numbers of connections. They're the hubs, they're the potential super spreaders, or people with very large number of connections. And any logic uses the Barabasi and Reka algorithm for constructing scale-free networks to connect people up. So you have these small number of hubs, and then most people have few connections, and the hubs often make a huge difference in the dynamics you see in the network, because they're simultaneously more likely to get infected and more likely to pass it on to someone else if they are infected, or be more likely to hear about a meme and more likely to pass it on if they have that meme. When it comes to contagion, they're key. So there's a bunch of different types of networks that are automatically built in by any logic. But generally speaking, for many empirically grounded models, you might want to make use of a user-defined network, which basically you construct. You actually shape it. You read it in from a PIEC file or a UCINet file, or some Gephi file, some package for social network analysis, and you impose it. And we have code that I've distributed to you, which basically allows you to do that. It can suck in a network and impose it in any logic from a PIEC file and from another file format. Quite easy to do. You can also have dynamic networks. These are static network types, and impose it. But you can have the network connections changing over time. The work of Martina Morris and Kretschmar, Deborah Kretschmar, I think it is, have really revealed in a striking way for SDIs that network dynamics makes a big difference in terms of connections starting up and going away, particularly concurrency. can make a big difference in spreading infections in a network. You could think of successive bridges. Right now I'm only connected with one other person, but if later I'm connected with a different person, I could bring infection from the first person I was connected with, and I'm the conduit for this other person. And you can pass around. Think about a baton in a relay race. You can pass that baton around, and it can spread quite a lot. So AnyLogic has some built-in networks, but don't go away with the misconception that these are the only network types. A lot of the time we build our custom networks based on social network analysis data that we have. We shape those networks. We have them evolve over time. And I've provided you with some code which does that, which has partnerships forming and breaking, or which exhibits associativity. So we can have people who are higher income hanging around with higher income people, lower income with lower income, or higher education with higher education, etc. Or people of similar ethnicity hanging around together, what have you. Okay, so there's ways of capturing this, but quite a few of them require some measure of code, and I've provided you some examples of that. Yes, Roberto?
When people, for example, are smokers, they're more likely to network with the smokers, and when they change the status,
Right.
they change their
Yeah.
network. So
That's right.
Can you reflect that as
Yes,
well?
yes, you can. Yeah. When I say can you reflect it, yes, it won't be a matter of merely picking it from a menu, but could it be captured? Could a Windchill or an Annie create you something to do that? Absolutely. Probably in a few hours, they could create something which would capture that phenomenon. Yeah. And in fact, code I've provided to you does that. In fact, it does that. And so your network evolves over time and evolves according to assortivity, and the assortivity could be based on properties which change over time. Okay. So yes, it's one of the challenges of changing risks when it comes to addictions. Is the fact that the addictions are socially embedded, right? And if I wish to quit smoking, I have to overcome the fact that many of my closest friends are smokers, those that I hang around, those that are in my support groups, whether explicit or not, they're fellow smokers. And it can require extra efforts to break out and actually shaping pro-social companions who will help in my same thing with drug addictions, and potentially there's even some overlap with mental health issues there as well. Changing our social context is always challenging, and yet it's often a mediator for success and failure of an intervention. And so, yes, we can capture that sort of phenomenon. Can you capture it without some custom coding? No. We'd want help of someone who feels comfortable in a bit of Java, but it can be done quite elegantly. I have provided code that is very closely related to this. Okay. Other questions about networks right now? Okay. So we have these networks in place. Let us now, before lunch arrives, make use of them. May we do so? Thank you. That's great. Okay, so ladies and gentlemen, what I'd like to do here is, okay. What I'd like to do is actually related to something that Roberto was talking about. He was a bit more sharp about it. But there's a covariation between our network companions, statistically, in our own, the habits of our network companions and our own habits. And this may reflect, in some cases, imitative behavior. I'm more likely to pick up habits that are consistent with what my companions have, or imitative behavior, behavior to change that is resisted by features of those around me. In other cases, it can mean picking companions who share my existing behaviors. I pick companions accordingly. So it's selection. And there's actually an interesting debate in the literature when it comes to interpreting results of like Christakis and Fowler on obesity and clustering of people by obese status. To what degree is that? To what degree is it selection? To what degree is it influence? You know, is it contagion of sorts or imitation? My colleague Ross Hammond of Brookings Institution has this nice little example where he looked at the published work of Christakis and Fowler and found that actually the data that they provide are not enough to resolve this issue, to resolve unambiguously which is it. There are other measures you could use that would more allow you to pick those things out, but they didn't think to record them. And one wonders, if they were to go back and look at the Framingham data, maybe some of those measures would be available. But in any case, we could more judiciously collect data to inform an understanding about which of these phenomena is dominant by choosing some appropriate indicators. Ladies and gentlemen, let's put in place an influence, a representation of influence, of contagion, as it were. So what I'd like to do is to go to person, and I would like to add in a function. From palette, I'd like to add in a function. And this function will be called is smoker. Yeah, are they a current smoker? Let's say is current smoker. Okay, are they currently a smoker? This is a function. Its job in life will be return a value, true or false. So we have to say it returns a value, and the value is, you have to scroll up a little bit, Boolean. True or false. Okay? It's going to be a function that's going to tell us, are they a smoker? We'd like to be able to do this crisply. Are we okay with that? Okay. We're going to return in state, am I in the state current person.current smoker. Actually, don't need to type person, but it's a good thing because you type in lots of other cases. So there we are. So the function will basically just be a shorthand for determining this. But we could just call it and not worry about how we compute it. It'll compute it. We'll just call is current smoker. Okay? Are we okay with this? Okay. Ladies and gentlemen, what I'd like to do now is I would like to go and drag in another function. With a function, it hides details, ladies and gentlemen. It encapsulates complexity. It lets you put some logic and hide it away in a place that, unless you want to see it, you don't have to see it. You have a nice name, you could say, just do your job. It will do its job, compute something for us, and we can use it with an economy of with real conciseness, economy of expression, without needing to litter our model again and again with certain complicated logic. So this one is going to be count smoking connections. Now this is getting a little bit crowded, so I'm gonna lift these up over here just so we have a little bit more room. Count smoking connections. What sort of thing do you think this is going to return? It has to return a value. What sort of thing if it's a count? An integer indeed. An integer, ladies and gentlemen. Indeed. I feel like Henry VIII or something. getting food delivered to me. Thanks so much. It's because I'm vegetarian, and if the veggie stuff disappears, then I go hungry. So I appreciate Jeff's kind ministrations. Okay, yeah, thanks a bunch. Okay, grateful. Okay, ladies and gentlemen, the body here will be something that even Winchell will get, about which even Winchell will get excited. Okay? Okay, ready? Here we are. Okay, so this is going to be connections dot. This is going to sound odd. Get connections. From these sort of connections, we can request all sorts of information. We're going to get a list of the connections, and then we're going to say stream dot filter and we're basically gonna ask which of them are a smoker, okay? For each person within the connection, note this little arrow thing, I'm going to ask, is the person a smoker? Person dot is current smoker, okay? We're going to call that, boom, just like that. And so this filter is going to take all connections and it's going to filter them down to just the current smoking connections, and then we're going to count those. Pretty nifty, don't you think, Winchell? Nifty or not? Oh, look at that. Is current smoker is not defined. Oh, yeah. Oh, I know why. Oh, it's a dumb thing. Okay. Sorry, folks. We have to do one more thing. And it's kind of a dumb thing. We have to do it. And there's a lot of things in life that are kind of like that. Okay, connections, ladies and gentlemen. We have to make it clear that this is a bunch of persons, not just any old agents. There's no echidnas in there. There's no platypi. There's no clinicians. It's all persons. So in the connections, we have to tell it the agent type as person, and that actually helps us with a lot of things. Okay, the final thing we have to do is mumble. Okay, yeah, this mumble. Okay, this has to return a long. Okay, great. Okay, what a fine mess I've gotten myself into. Okay, so this goes to other, and it's actually a long that it returns, which is a value which can be bigger than an int. Okay, now we're in happy camper state. Okay. Too bad there's not a version that returns an int. But no. Okay. Okay, so let me put up this code, and I'm going to walk you through it. Ladies and gentlemen, of the connections, it asks for the list of those connections. This stream basically turns it to a way we can do this nice stuff. It filters those down to only include those which are current smokers. It's basically filtering to only have those that are current smokers, and then we count the number of those. Are we okay with that? This is ladies and gentlemen, this thing here with the person arrow, we're actually telling it, this is a function. It says, given a person, I'm going to return true or false in this filter. So filter needs something that takes a person and tells me, do they pass the test to be included? Do they pass the test to be, or are they to be filtered out? Do they pass the criteria? And this is a function that says, given a person, we're going to return true or false. Based here, are they in fact a current smoker? Are we okay with that? Okay or not? Okay. Thank you. That's great. Excellent. Next. Okay, that's as bad as it gets. And believe me, it's less bad than doing it another way in my book. Okay, ladies and gentlemen, we're going to go to initiation here. And what we're going to do is We are going to have their likelihood of initiating be dependent on the number of their connections that are smokers. What do you think? Great. Great. Okay. So, ladies and gentlemen, we are going to add to main a kind of beta term for this, okay? We're going to go up to main, and we're going, just like we had this mortality hazard beta, we're going to drag in a parameter to main that's going to be initiation hazard beta for count smoking connections. And by default, that will be 0.1. 0.2. Okay? So if I have 5 connections who are smokers, we're going to multiply it by this beta, get 1, and it's going to be exp of that. So it's going to be, my chance of smoking is going to be increased by a factor of 2.7 or so. My hazard rate of smoking. What do you think? Good or not? Okay. Okay, ladies and gentlemen, let's go back now to initiation. And now let us reap the benefits of our labors. Okay? Okay. Okay. Okay, here we go. So we are going to now add in a term here. There's a baseline initiation hazard by age. And now I'm going to add in a term. It's going to be an exp. We're going to multiply the initiation hazard for smoking connections by the what? That's the beta, and we multiply it by what? The count. Count smoking connections. There we are. So let me put this up on the big screen. This is what was there already, ladies and gentlemen. The thing that's up here was here already. All I did is I added this. So here, if we have count smoking connections 0, what is this whole thing going to be? It's going, well, yeah, this is going to be 0. And so this times this is going to be 0. And exp of 0 is what? Exp of 0 is 1. So it won't increase it at all. But as the count of smoking connections rises, we're going to have a larger and larger thing here. And we're going to be, the exp of it is going to be, this is a thing that's larger than 0. It might be 1, it might be 2, it might be 3. And exp of that is going to be greater than 1. So it's going to be, this whole thing is going to be multiplied by something greater than 1. It's only going to be 1 if I have 0 smoking connections. The more smoking connections I have, the higher the likelihood that I'm going to start smoking. What do you think? Good or not?
Yep.
Run or not? Run. Okay. 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 I might assure you that not everyone in Canada talks like that. Okay. Ladies and gentlemen, run. Here we go. Okay. So what should we start to see? What would you expect to start to see that would be different from what we've seen henceforth? We'd expect. Oh, wait a minute. Wait a minute. So what's going on here? Why aren't I seeing connections between people?
It just gives
Thank you. I don't know how in the world I missed that. Was there the network there at first? Yeah, okay. Okay, it only gives it to the first generation. We need it to be every generation. How are we going to do this? Well, it's very straightforward, ladies and gentlemen. It's very straightforward in its simplest form, and it's fairly straightforward in a more performant form. So every time someone is added to the population, and this is the most simple way of doing it, we're going to recompute the network. Now, that's not going to be highly performant. In other words, it'll be somewhat slow as our population size rises, and we'll have to figure out better ways. But let's do that because lunch beckons. Okay? Okay? So, ladies and gentlemen, what I'd like you to do is go, when we add people to the population, where do we add people to the population? Riddle me that.
Immigration of the.
Yeah, immigration and birth. The initial population is taken care of already. That's wired up. It's right here when we add them. So all we're going to do is we're going to say here, main, by the way, that's where I am, so I don't even have to say that here, but main dot, and we're going to tell it basically apply the network. Apply network. Okay? Oh, hey. Apply network. I think that should work. I don't know why it's... No, main. Oh, of course, main can't be resolved here because we're in main. Okay, fine. I thought I'd use a uniform principle, but a nice hope was dashed by ugly fact. Okay, this dot apply network, or I could just say apply network. That means recompute the network, okay? Now for a distance-based network, the network is deterministic, so it's going to be fine. This wouldn't work so well for a random network or scale-free network, etc. Okay? Okay, so this is an immigration. Yes?
Is there, between the new code and
Yes.
the old code, is there a semicolon?
There is, and that's needed.
Yeah.
Because these are telling it to do something. Add a person to the population, apply the network. We're telling it, do this. We're making a command. It's almost like we need an exclamation point. Okay? The other place we need to do this is where? Yes, birth. And birth lies in person. Now, incidentally, this is, well, okay. Anyway, I won't dwell on that. Okay. So here we're going to have to do main.apply network because it's main that knows how to apply it. Don't say person, don't leave it out. If you do that, then it won't actually apply the network. It won't weave them in. We have to ask main to do it. Are we ready? Good or not? Okay. So shall we run it? Run or not?
Yep.
Run. Okay. Sorry, do you need me to pause a little bit? So right after add population, I'm putting this. Right after the add population, I'm putting that. But in fact, it can go here, anywhere along here, because we can do it after we add them to the histogram, but we have to do it after we add them to the population, because that's when the baby will be present. Okay? Are we ready to run it? Okay. Let's run it, ladies and gentlemen. Let us compute. Okay, here we go. Okay, here we're running it. The network is evolving. People are coming in. People are becoming smokers. People who were smokers are quitting. But right now we don't have quit defined in terms of this. It's just becoming a smoker. Now, if we had clustering coefficients, what we'd likely see is that compared to the earlier network, the smokers tend to be more clustered near each other. Okay, but I don't see very strong impact of that. Let's up let's up the beta for count smoking connections. I'm going to raise it to be 0.5. Okay? So all it takes is 2 connections for me to have over a 2.5 times chance to become a smoker myself. Okay. People are still quitting smoking. It doesn't change that, but it's really the initiation side. Okay. Here we're getting some plausible clustering. Let's go on the far side here. Okay. We have trouble seeing because the network's in the way. How would we change that? How would we have the network appear behind people? Anyone remember? Yeah, we could go to person, go up and say, hey, have the network appear behind people instead of in front. So we go to the connections, we go down and we say draw behind agents. Are we okay with that? Okay. So what we should see here is a larger amount of clustering. Okay, now the network's in the background here. And we would need statistical tests to be able to help validate this. But to my visual cortex, it suggests to me a measure of clustering of smokers here. Do you see this? There's sort of a group here, a group here, a group here, right? Okay, now in the final moments before lunch, suppose we wanted to now have SES further have some impact on initiation. Could we do that? Could have an SES beta term that's multiplied by SES associated with this initiation hazard. Okay, now we'd have to be careful with that. We'd have to control for the effects of number of people smoking while at the same time, SES, but we could imagine a study that would do that. Let's go over to main. Notice what I just did. I just clicked on one of these and I held down control and I dragged and it duplicated it. So this would be initiation hazard beta for, and instead of count smoking connections, for SES. And I'm going to make it 1.0. So if I compare an SES of, minus 1.0. If I have an SES of 1, compare an SES of 0, having an SES of 1 lowers my probability, my hazard rate for initiating smoking by a factor of 2.7 times. Because SES of 1 times this would be minus 1, SES of 0 was 0 times this, and basically then we're going to have exp of minus 1, which is 2.7 times smaller than 1 itself, exp of 0. Are we ready for this? Okay, we're just about ready, which is good because your bellies are just about ready for lunch, I think. Okay, ladies and gentlemen, let's go to initiation. And now let us expand our components here. Hey, come on. Okay, here we go. Boom. Okay, so I'm going to write this out. Now, instead of just having that, we're going to have a further term. And I'll put it down here. Plus, I'll actually put it plus, and this is going to be something like this. Initiation hazard beta for SES times what? SES. My SES. That's all there is. Okay, and then that's fine. Notice here it's matching up the parens. This paren match that paren. This paren match that paren. We're in fine shape. So these are the types of relations that come out of a survival analysis or a competing risks analysis. So you have exp of a beta times, in that case, covariate, plus beta times another explanatory variable, etc. Are we okay with this? Do you want to run it? What should we see now? Well, suppose, ladies and gentlemen, let's first turn off. Oh, well, this is interesting. Windshield. Let's mumble. Okay, pardon me, I'm exhibiting computational distress. Okay, mumble. Okay, okay, fine. I'll quit AnyLogic, boom, and I'll come back. I saved, and I'll come back into AnyLogic. Here we go. Development, come back into there. That was a curious type of dysfunction. Okay, ready? Okay, you folks can run it at your pleasure, but I'm currently just calling this back up, and then I'll run it. But it'd be nice to run it with no impact first of social impact, just of the other impact. Okay, the impact of SES. So let's have and this is one of the things we do to learn from a model. So here's our population 1,000. I'm going to create, you notice that it's actually best to have population 1,000. Okay, I got to be really careful. Winchell knows why. Okay, I got to be really careful here. Baseline. And I'm going to return all these. Notice that in AnyLogic it highlights things that you've changed from the default values. Okay, ignore that. And I'm going to return these to their default value. Okay, pretty sure the default value of this was 0, and it's still highlighting it. But here we go. Oh, what was the default value of this guy? Well, I can go check. What is it here? 0.2. Okay. I'm going to have. Okay, so this is 0.2. I'm going to make a copy of this. Copy. And I am going to paste it in. Boom. And I will have this be population 1,000, only SES, boom. And therefore I'm going to have no impact of smoking connections and just leave the -1, okay? And so I've eliminated the effect of smoking connections. And I can ask, if the world were this way, what sort of gradients would we see, or what sort of patterns? And then I could copy that, and I could paste it, and I could have another controlled computational experiment, which says population 1,000, only social influence. No effect, ladies and gentlemen, of SES. Ooh. Okay. Okay, I've got to be careful. Okay. And I'll turn this to, we ended up wanting to do it at 0.5 instead. It'd be kind of nice if we can use 0.5 as our baseline value. I'm going to go in and change the model's sort of default value to be 0.5 just so that we can use that. I think it's a cleaner thing. So model initiation beta, I'm going to make it 0.5 here. I've changed the default value just because I want to be able to see it visually for us. So I've changed this to be 0.5 here, and now I'm going to go back to these experiments. So for the baseline, it has a value of 0.5. I changed the default value. Only SES has a value of 0. There's no impact to count smoking connections. SES has influence. Only SES influence, 0.5 for count smoking connections, 0 for beta. And then I'm going to have a final one, which is going to be, I should have copied. It will simplify my life. I'll copy one of these guys and paste it in. Here we go. And there we go. And I'm going to have both SES and social influence. Save. And I'm going to change this beta for SES to be minus 1.0. Oh, excuse me, minus 1.0. Huh? Windshield, did you see that? Happy. Huh? Okay, I don't. Mumble. Mumble. Okay, get it out of there. Okay, I just saved it. Okay. Are we okay? Are we ready to run these 4? And then we'll enjoy our repast. Okay? Okay. So here we go. We're going to run the baseline. The baseline is both, doesn't it? Okay, let's run it with only, let's run it only with both on. That is, in fact, this sort of baseline. Okay, run it with both. What are we going to see? What do you think we'll see here? Well, if we go over to the high SES, what should we expect to see? Less smoking. How about the low SES? Proportionally more smoking. Why? Higher SES are less likely to initiate by a factor for the extremes of about almost 3 times for the extreme of the network. But we also see clustering, and that clustering builds on itself in a path-dependent way. If you have a cluster, it builds on it. So if it gets established, it starts to build on itself. Maybe we do see a somewhat larger prevalence, but it's not incredibly obvious because there's this feedback as well among individuals attracting. Basically, if I'm a smoker, I start converting people around me to be smokers, right? And they start initiating. And then once trapped, they can quit, but then they can also fall back into smoking. So here it's not obvious that the SES grid has maintained. Let's only look at the SES. No social influence of smoking. What would we expect to see then? Well, a gradient, ladies and gentlemen. A gradient. Here we go. Some gradient, I would expect. Maybe I'm missing it here. It's not obvious that there's a striking gradient. What do you think? Did I miss something? Let's try this.
Population's increasing, the higher SES.
The population is increasing. The higher SES, yes. People are coming into the higher SES population. Okay, so that's a confounder here. There's people coming in who carry with them certain status. How would we control for that? Well, we could turn off immigration, right? Turn off immigration. We should have created another experiment. Here's SES with no immigration. What might we expect to see? Well, we wouldn't see it at first, but we should see it emerge over time. Some influence of SES on smoking. Some general sort of gradient where we have fewer smokers in the higher SES category and somewhat more in the lower SES category. Not terribly pronounced, I have to say. Okay, perhaps it's a matter of the relative values here, but I don't see a really pronounced gradient. There may be a little bit more here but it's not a huge amount. Let's give it a bit of extra time. People are being born in. They're starting to smoke. Okay. No social elements here. Maybe a little bit more down here, but and a bit less up here. But it's not incredibly pronounced to me. Let us go and say, okay, make sure we're understanding, make sure it's working correctly. Make it even stronger influence of SES, -2. So now someone who's high SES is perhaps 8 times less likely to initiate smoking than someone who's low SES. Here we'd expect to see a much bigger gradient emerge. The people up here should be quite protected from initiation. The people down there, less. Now you notice we started the population in a random state with respect to this, regardless of SES. So we have some individuals who are starting smoking in the initial population, and they're not going to go away. They may alternate back and forth. But as new generations come in, I would expect to see rather more smoking in the low SES group. And there does seem to be somewhat more clustering of smoking down here, or somewhat more prevalence of smoking. We could look at some statistics to quantify that. A little bit hard to make out right now. Okay, here's only social influence. So by the way, I should return those parameters to the values. I changed them and I'd like to change them back. Okay, okay, let's try that again. Boom. Okay, and now, let's change this back immigration rate, since we changed it, but we didn't mean to permanently change it. We were just exploring. Great. Now we'll look at only social influence. Only social influence. Now we should see a more dominant clustering effect becoming obvious over time. As people coalesce around certain points, smoking begets smoking, and you will see sort of this emergence of these clusters. And these clusters will end up spreading because their periphery will end up influencing people further out, and eventually you're going to see a large fraction of the population starting to smoke here. You know, the cone of current smokers is really, really rising here. And I would hazard that if we run this out a long way, some of that is just growth of the population. But if we were to run it out a long way, we would end up seeing a large fraction of current smokers. You notice this pie graph is more instructive than the numbers. We see current smokers being 43, 44% of the population, 45. Soon they're going to be a dominant component of the population. We could have constructed similar graphs for each SES stratum before, each high and low. That would have been instructive. Here we have a very high preponderance of smokers, just because of this contagion effect. And they are clustered, but those clusters spread. Social influence, ladies and gentlemen. People's networks here are influencing them. But not only that, we also have the glimmer of a different type of social influence, namely familial influence, in the form of the mother passing on characteristics to her child in the form of what? SES. And we will complete the picture there to address Rod's question after lunch by passing on a mother's smoking status as a factor that might influence her child to be a bit more likely to engage in initiation. Okay? So there's some influence intergenerationally, behaviorally, there that's imitative within the family, and particularly the privileged relationship of mother to child. Okay? Thank you very much. Lunch is served, and we will come back in how long, Jeff? Half an hour. Great.